let us calculate some Maclaurin series. This is a formula that allows us to write a power series based off of a differentiable function. And if all goes well, the series that we've got will actually converge to the function that we started with. It's not guaranteed to happen, but for today, let's just practice calculating our series coefficients. The first function that I'd like to look at is the function sine of x. To calculate a Maclaurin series, I want to look at the successive derivatives of this function. For this exercise, I only want to find the first 4 entries, so the constant term, the linear term, the quadratic term, and the cubic term. The powers of x are going to be the 0th power, the 1st power, the 2nd power, and the 3rd power. So I'm going to build a table where I look at the values of n, starting at 0 and going up to 3. If I start at 0, those are the first 4 integers. Now for each value of n here, I'm going to calculate a derivative. So I'll say that in this column, I want the number n derivative of my function. Now I'm choosing to write this in the notation n in parentheses as the superscript to my function f, and that denotes the number n derivative. It would be a little bit difficult to express this idea with the tick mark notation, right? How do I have f with an arbitrary number of tick marks to denote an arbitrary numbered derivative? I think I'll stick with the superscript notation this time around. So for the sine function, this is not a difficult calculation to make. The 0th derivative of the sine function is just itself. I have taken 0 derivatives so far. The first derivative of the sine function is the cosine function. To find the second derivative of sine of x, I take the derivative of its first derivative. The derivative of the cosine function is minus sine of x. And then to find the third derivative of the cosine function, to take the third derivative of the sine function is just the derivative of its second derivative. So one more derivative here, and I've got minus cosine of x. So here in my table, I have the first bunch of derivatives of this function. And now I'm going to evaluate each of these at the number x equals 0. So sine of 0 is, of course, 0. Cosine of 0 is 1. Minus sine of x, well, that would be negative 0, which is just 0. And then minus cosine of 0, that would be minus 1. Yeah? Now these numbers are going to go into the Maclaurin series formula. So the term I'll have here is x to the power n. The coefficient I have is a fraction. The numerator is the number n derivative of my function I started out with, evaluated at 0. The denominator is n factorial. So I'm going to use this chart to help me out here. For my first term, my constant term, Well, I'll have a numerator 0 divided by 0 factorial. Just as a reminder, 0 factorial is the number 1. And this will be multiplied by x to the 0 power. So it'll just be a constant. And for this Maclaurin series, the constant term is 0. Moving on, for n equals 1, I'll have a numerator of 1 and a denominator of 1, all times x to the power 1. So I'll get just an x. For n equals 2, I'll have a numerator of 0 and a denominator of 2 factorial, which is just the number 2, all times x squared. So my quadratic term is going to be 0x squared. And finally, for n equals 3, my numerator is minus 1. My denominator is 3 factorial, which is the same as the number 6. And this is all times x cubed. So here are the first 4 terms of my Maclaurin series, including the terms that just work out to be 0. Constant term is 0. Linear term is x. Quadratic term is 0x squared. Cubic term is minus x cubed on 6. Let's look at a different function. I'll keep most of this table in place, so the method of calculation is going to stay the same. Just the particulars will change because I'm looking at a different function now. Let me get rid of these and these and these. And this time I want to look at the function e to the power x plus 1. Now, like I was saying before, I need to take the successive derivatives of this function. The 0th derivative of any function is just itself. I have not taken any derivatives just yet. The first derivative of the function is what I get from just doing an ordinary derivative. Here, the exponential function is its own derivative. And the chain rule tells me that because my exponent is the function x plus 1, I need to multiply by the derivative of x plus 1, which is just 1. Well, that was going to tell me that the derivative of this function e to the power x plus 1 is itself. Multiplying by 1 didn't really change anything. So the second derivative of this function is also going to be e to the power x plus 1. The second derivative is the derivative of the first derivative. I've already figured out that the derivative of e to the power x plus 1 is still e to the power x plus 1. And that's going to be true for the third derivative as well. So in this example, my successive derivatives all have the same formula, which is pretty nice when it comes to my next column here. If I evaluate this formula at 0, I'll get the number e, the exponential number. And I'll get that same value for each different derivative because they happen to have the same formulas here. Now I'm going to take these numbers and find the terms in my Maclaurin series. Again, I'm just looking for the first 4. This is just an exercise. So the number 0 term in the Maclaurin series has a numerator e and denominator 1 times x to the power 0. So that's really just constant term e. My number 1 term in the Maclaurin series has numerator e, denominator 1 again, This time it's 1 factorial, but that's still the number 1, times x to the power 1. So I'll say this is e times x. For the number 2 term in my Maclaurin series, I'll have numerator e and denominator 2 for my 2 factorial times x squared. I don't really need to simplify this anymore. And then for my number 3 term, I'll have numerator e, denominator 6 times x cubed. So here are the first 4 terms in the Maclaurin series for the function e to the power x plus 1. The constant term is the number e. The linear term is e times x. The quadratic term is e divided by 2 times x squared, and the cubic term is e divided by 6 times x cubed. Let's keep going. So I'll pick a different function here. I'll calculate successive derivatives, and I'll see what I get for my Maclaurin series. I'm going to look now at the natural logarithm function. One thing I need to be careful about is that Maclaurin series are always centered at x equals 0, meaning that I need to evaluate my function and its derivatives at x equals 0. Oh, just 1 minute.